All right, and here is chapter 10 for general chemistry. This chapter, we're really going to be thinking about electrons. And so, before we get thinking about electrons, we have to first talk about the electromagnetic spectrum and electromagnetic energy. And so, to think about this, we're really going to talk about light. And light itself is both a particle and a wave. And Sir Isaac Newton back in the day figured out that white light actually consists of individual colors of the rainbow that are all combined together. So when we're seeing a white light, like especially from the sun or from a light bulb, that really contains all different colors within the rainbow combined together. He also figured out that light was composed of extremely tiny particles traveling at high speeds, according to Newton's laws of motion. And so, because of that, we were then able to kind of think about light in a new way. It's an energy that contains both a particle of energy and it also travels on a wave. And so, on a wave, we have what are called wavelength, frequency, and amplitude. And wavelength is the distance between two peaks or two troughs in a wave. The frequency is the number of wavelengths that pass a given point in a unit of time. And typically that's going to be a second. So, how many waves pass through a given point of space in a second would be your frequency. And then the amplitude is the distance from the middle of the wave up to the peak, or from technically the middle down to the trough. And so, if we multiply the wavelength times the frequency, that equals the speed of the wave. And so for electromagnetic radiation, the speed of a wave, or the speed of light technically, is 2.998 times 10 to the eighth meters per second. I don't need to have you to have that memorized. What I do need you to know is that wavelength and frequency are inversely proportional. That means that as the wavelength increases, the frequency decreases, and vice versa. So, when we think about wavelength, frequency, and speed, they're all traveling at the same speed here. The big difference is if you take a look, that first wave up here at the top left, that has a pretty long wavelength. Okay, so from peak to peak, you can see the wavelength is denoted by that black kind of bracket on the top. And so its frequency is right around 3 hertz, or 3 cycles per second. Now, as we go to the middle, you've decreased your wavelength. Your wavelength is now smaller. And so, because of that, our frequency goes up. We can have more waves passing through a given moment in time in 1 second. And then, as we get even smaller, that very bottom one, you now have an even higher frequency. So that's what I need you to know, is that as wavelength goes down, the frequency goes up. On the right hand side, all that is showing you is different amplitudes. So amplitude is how tall that wave is from the middle to the peak. Now, we are going to talk about the electromagnetic spectrum here just for a little bit. The electromagnetic spectrum is a range of all types of energy that travel in the form of light. And it's very odd because in our everyday life, we think of light as just being the light that comes from, for example, the sun, or from our TV, or from light bulbs. We typically think of that as light, but in reality, the electromagnetic spectrum is so much larger. So, the lowest energy, or the longest wavelength light, is a radio wave. And so radio waves are used to obviously communicate our information, from music to also just like walkie talkies. And a little bit into other communications like that. Then, as we get a slightly smaller wavelength, we now move into microwaves. And so now microwaves are even smaller, but they're still actually pretty large. Now, we can't view either of these. Our eyes are not good enough at viewing either of these. And as we get smaller and smaller, we move into infrared. Now, infrared is used for like our remote controls for our TVs. It can be used for like night vision, that sort of thing. Some animals can see into the infrared spectrum, however, we cannot. Infrared also won't really harm our body, so it's unlike ultraviolet on the other side that can harm our body. Now we get into the interesting part. The interesting part is the visible part of the wavelengths. And so for visible light, that starts with our red light being the lowest energy, moving on into our purple violet, which is the highest energy. And so when we get to ultraviolet light, we are now past the violet that we can see, and now that energy becomes higher, or high enough, I should say, that it can actually harm our bodies. So ultraviolet light we know is in the sun's rays, and that's why we wear sunscreen. We also have X-rays, which are even smaller in wavelength, higher in frequency. And so we now move into X-rays, which are used for medical imaging, other uses as well, but medical imaging is the main one. And then finally into gamma rays. Gamma rays are very, very harmful. They can do quite a bit of damage to our body. So, how do we use light, or why do we even care about light? Well, there was a guy named Bohr, and what Bohr did is he took hydrogen atoms and he excited them. And when he excited them, he gave them some energy, and those electrons in the hydrogen atom started to bounce up to higher energy levels. So, this electron here, the green dot, moved from n equals 2 on up to the 3. But it doesn't want to be up there at 3. It wants to be back down at 2. And so in order to come back down to 2, what has to happen is you have to release some energy. And the energy came out as a form of light. And so what he was able to do is he was able to excite hydrogen. He was able to measure the energy of all those wavelengths of light. And he was able to figure out that hydrogen atom electrons, I should say, the electrons specifically, have different areas of the atom it would like to take. And so we came up with the Bohr model. And so you might have learned about the Bohr model in previous science courses. The Bohr model is the most simplistic way that we can think about where electrons are. Now, it's important to know that the Bohr model isn't actually what's happening. We don't have electrons just spinning in circles in these certain paths around the nucleus. What really happens is that we get kind of this density of electrons. So on the right side, you can see what's called the electron cloud. We can see where those electrons are most likely to be on the right side. So the Bohr model is very great at starting to understand that electrons have different energy levels. They are different distances away from the nucleus, but it's important to recognize that the Bohr model is just used to kind of get our minds going. It's not specific enough to give us all the answers. Now, we need to start thinking about the electrons and their energy. So electrons can only exist in discrete energy levels, but not between them. So they can exist on level 1, 2, 3, 4, 5, and so on, but you can't hang out in between. They've got to be at one or the other, and they can jump from one to the other. And when they do that, they release some energy or they gain some energy. So we're going to talk about the principal quantum number. We're going to talk about how to tell where an electron actually is. We're going to give it an address system. So this principal quantum number can really be thought of as kind of like the zip code. It's the first way of narrowing down where an address is. Okay, in Oshkosh, for example, we have 54901, 54902, 54904. We have different zip codes, and that can start to narrow down where this address might be. So the energy levels are labeled with an n value, n just meaning a number, where that n has to be 1, 2, 3, all the way up to 7. And so generally speaking, the energy of an electron is greater for the larger numbers of n. So the energy of an electron that is in the level 3 is higher than an electron in the level 1. And so that n is referred to as the principal quantum number or the shell number. And that really defines the location of where it is on an atom. So 1 is closest to the nucleus, 2 is a little further away from the nucleus, and 3 is further yet. So it kind of looks like this. The further away from the nucleus you go, the higher the energy you are. But it's important to know that when we actually talk about electrons, they aren't going to be in these circles, but those circles tend to help us figure out how far from the nucleus they will be. Now we've got sublevels. Within the numbers 1, 2, 3, 4, and so on, we have more levels than just a number 1 or just a number 2. we have these sublevels. And the sublevels are letters S, P, D, and F. All right. And now, if we think about our addressing, the N number, the 1, 2, 3, 4, and so on, that's kind of like our zip code. It gets us onto a certain area. Then you can think of these letters S, P, D, F. You can think of that as the street number. And so the street number, or sorry, the street address, the street name, really narrows down within that overall area. Where are we in more exact terms? And so the principal energy levels have different number of sublevels, and it just depends on what orbitals they have. So the first level just has one sublevel. It's just got the S. Then the 2 has two sublevels. It's got the S and the P. Then the third sublevel has three subs. It's got S, P, and D. And the fourth has four sublevels. It can have the SP, the D, and the F. And so each of these orbitals or each of these sublevels have different shapes. And the S orbital is a nice spherical shape, okay? Then the P orbital, I kind of call these dumbbells. They kind of look like dumbbells if you were to think of a weight. And they've got three p orbitals. So the S has one sphere. The P has two kind of dumbbells on each, but there are three of them. And so those three all come together. And then the D's and the F's get a little more crazy. The D's I kind of like to call the four-leaf clovers, and then the F's are just crazy. So these are the actual shapes. Bohr thought they were more of like a ring of kind of Saturn going out, so different rings. In reality, his model works just fine for telling us how far the electrons are going to be from the nucleus, but the electrons are whizzing around in these types of shapes. So kind of a sphere for an S, kind of in these dumbbells for a P, kind of a clover for a D, and then these weird ones for an F. So again, the number 1, 2, 3, and so on, that tells us how far from the energy level it is. And then these letters kind of tell us what shape it's going around the nucleus in. And so there's this guy named Pauli, and Pauli came up with the exclusion principle. And what he said is that no two electrons in the same atom can have the exact same location and spin in an atom. And so we can have two electrons that are in one s orbital, but in order to have two in the 1s orbital, we need to have them spin in opposite directions. So electrons can both be in the same orbital, for example, the 2s or the 1s orbital, but they need to spin in opposite directions. But that's as high as we can go. Each orbital only holds up to 2. So if an orbital needs to hold 2, if one of those shapes here needs to hold 2, one electron is spinning up and the other is spinning down. And so if we take a look, this s orbital here can hold 2. The p orbitals, we've got 3 of them, so 3 times 2 gives us 6. The d orbital can give us 10. 5 times 2 gives us 10. And the f orbital can give us 14, because 7 times 2 gives us 14. So, again, to reiterate, we have the number that goes in front. That's kind of like our zip code. Then we've got the street name. That's kind of that PSD, that sort of thing. And then we've got the spin. The spin really narrows us further down onto that street by kind of giving us like a number. So to put it all together, we're going to do this using electron configurations. And so in electron configurations, it's that address for an electron. The energy of the atomic orbitals increases as we move away from the nucleus. And so a orbital with the number 3 to start is higher in energy than a number 1. 5 is higher than a number 2, and so on and so forth. And that is because those electrons are further from the nucleus, which means that the nucleus isn't pulling on them as much. If you remember back, protons are positive and electrons are negative. So they want to be attracted to each other, but the further you move away, the less attraction you have. And that's just like a magnet. The further you are from a magnet, the less attracted it's going to be. And so if we think about those orbital energies in the atomic structure, the different letters have different energies. Our S is the lowest. Our P has the next highest energy, D has the next highest energy, and F has a really high energy. And that all has to do with those electrons trying to get away from each other in those orbitals. So this diagram here just shows us the energy. The higher up on this chart you are, the higher your energy you have. If you take a look at the kind of the capacity, all of your S's can hold 2 electrons, all of your P's can hold 6, your D's can hold 10, and your F's can hold 14. But if we take a look, the S's are always lowest of the number. Okay, so 1S, 2S is next lowest, 2P is next lowest, 3S, 3P, 4S, 3D, then 4P, and so on. All right? And so if we think about how to write an electron configuration, we first need to start with that number. Now that number tells us what level we're in. Then we're going to give us uh, a letter, okay, so S, P, D, or F, and based on where we are in the periodic table, it will tell us where we are. So there's an S area of the periodic table, there's a P, a D, and an F. And so that letter tells us where we're going to be. And then the superscript, which is a smaller number that is higher and to the right of that letter, will tell us how many electrons we have. And so if we take a look at how to draw these out, these arrows are representing electrons. And so this is hydrogen. Hydrogen has an electron configuration of 1s1. It's the lowest electron or lowest energy electron on the periodic table, and it just has 1 electron. We know that hydrogen has an atomic number of 1, and so its neutral atom is just going to need 1 electron. So 1s1. If we think about the energy of those electrons and where they need to be situated, it's just 1 electron, so it has to be in the 1s1. Now, as soon as we start to add in more electrons, we're going to have to put opposite spins. But you always need to fill the first electron energy first. So helium is the next element past hydrogen. Helium is going to add 1 electron. And so now we're in 1s2. The only thing that changed from hydrogen to helium is this number 2. Okay? And those electrons now need to go up and down. Lithium, however, adds 1 more electron. But we can't hold 3 electrons in the s orbital. So we need a 1s2. And then we need 1 electron in the 2s orbital. Okay, so the 1s is full with 2, and then we add 1 more to that s. Beryllium adds another electron. That now is going in that 2s, but now it's a downward spinning electron. So now we've got 1s2 and 2s2. The s's are full with 2. When we need to go to boron, boron has 1 more electron than beryllium. And so because of that, we now need to add on that new energy level. Okay, so at this point, we have a 1s2, a 2s2, and a 2p1. The p region is over on the right-hand side of the periodic table. It's from groups 13 to 18. Okay, so the s's are the first 2 columns, the p's are the last 6 columns of the periodic table. Carbon adds another, nitrogen adds another, on up to neon. So you'll see neon here is filled with 1s2, 2s2, and 2p6. If you want to see even more, you can go into your book, and this is section 10.4, I believe. And so you can go in your book and you'll find the exact pictures of all the first 18 electrons. And so, yeah, this is, 10.4, yes. And this shows you all the different arrow diagrams, the orbital diagrams, and it also shows you their electron configurations, which are, again, these number and letter combinations. So, rules to writing electron configurations. You can have no more than 2 electrons occupying an orbital. So if you have an s orbital, it only holds 2. So you can't have 2s5. That doesn't work. It's 2s2. Then the electrons are going to fill the lowest energy orbitals before filling the next. Each orbital in a sublevel has 1 electron to occupy it before the next. And that's, again, used more for orbital diagrams. You aren't really going to do too much of that when it comes to the numbers and letters. And then the number of electrons in an electron configuration must match the number of electrons in the atom. So 1s2, 2s2, 2p4. The 2 plus 2 plus 4 gives us 8 electrons. That gives us oxygen. All right. So this is how we fill our orbitals. We fill the 1s first, then we fill the 2s. Okay, so what's kind of happening here is we're going 1s, back on up, fill the 2s, fill the 2p, then the 3s, then the 3p, then the 4s. And now is where it gets kind of weird. We got to hop back down to 3d, then back up to 4p, then up to 5s, and so on. And it all has to do with the energy of those electrons. Remembering that those more extreme electron configurations of like the D and the F, those have high energy because there are so many electrons in there. Now, this is what I would love for you to kind of draw out on a periodic table that you have. So in this region here, this is called our S block. And so the first two columns plus helium technically over on the far top right, those are all going to be S's. Then we've got over here on our right-hand side, this is our P block. Our P block are the last 6 columns. Our D block is right here in the middle. And our F block here is at the bottom. And so in order to do these, what you need to take a look at is what we're passing through. So to get all the way down, I'm going to clear this. And let's do, for example, we're going to do argon. Okay, so argon is way down here. In order to get to argon, you're going to write down exactly what we passed through. So we're starting here. We've got our hydrogen and helium, 1s. Oops, sorry, that's a 1. Going down to argon. We start here with hydrogen. We get a 1s. And since we pass through hydrogen and helium, we have 1s2. Then we're passing through our lithium and beryllium. We go through a 2s2. Then we need to pass through all of boron through neon. That gives us a 2p and 6 because we passed through all 6 of them. Then we are passing through sodium and magnesium. That's a 3s2. And then we pass through aluminum all the way to argon. In this case, since we passed through all of them, we get a 3p6. And so all those letters together, this would be our electron configuration for argon. Let's say we just want to go to boron. Boron, we're crossing through 1s2, 2s2, but since we're stopping here at the first cell of the P, we only need 2p1. And you can kind of see that up here in the corners of this diagram, 1, 2, 3, 4, 5, and so on. In the middle, it goes all the way up to 10, and down here it goes up to 14. Those can help you figure that out. All right, so let's practice some electron configurations. Again, please pause, try these on your own, and then we'll come back. All right, so the first one is carbon. Now carbon, I'm going to draw a really rough sketch of the periodic table up here. Okay, so carbon first needs to go through hydrogen and helium. So it needs a 1s2. Then it's going to pass through our lithium and beryllium. So it's got a 2s2. And then it comes on over here and it stops 2 into that first P block. So it gets a 2p2. Again, it's stopping there. So that's where we're going to stop our numbering. So our answer here would be 1s2, 2s2, 2p2. All right. If we think about sodium, sodium is down in the third level. So we're going to need everything that we already did, except now, if you watch up at my periodic table, we need to fill that whole 2p. So we have 1s2, 2s2, 2p6. And now we come down into the third level, and we're sitting right on top of sodium. So sodium there is a 3s1, and that is our electron configuration for sodium. And then chlorine. Chlorine, we got to keep on going. So 1s2, 2s2, 2p6. We need to go through all of the 3s, so we go 3s2, and now we're into the 3p. And so now down in our 3p, we're stopping here almost towards the end, and we filled up 5 of those, so we get 3p5. Now, this is going from name into electron configuration. We can also go from electron configuration into name. And so this is kind of like going in reverse. You're now going to follow through the periodic table. I think it helps to use your finger on the periodic table and stop where it finally ends. So pause this, take some time, work on it, and then come on back. All right, so here, 1s2, 2s2, we only need to go through hydrogen and helium, and then lithium and beryllium. And so we end here with beryllium as our final answer for that one. This next one, 1s2, 2s2, 2p6, 3s2, 3p4, we've got to go through hydrogen and helium, lithium and beryllium, boron to neon. Then we've got to go through sodium and magnesium. And now we're finally moving through aluminum, silicon, phosphorus, and we end here on sulfur. And then this last one, we don't have as much. We didn't go through as much. So technically, we can kind of hop back for past our sulfur. And so we're ending at the 3s orbital. 3s2 is the end of that. And so the end of the 3s orbital is magnesium. All right. But why do we have these patterns? Why is the periodic table organized the way it is? It all has to do with kind of your valence versus your core electrons. So the valence electrons are the outermost electrons. So if we think about something like our sodium, or sorry, our sulfur, 1s2, 2s2, 2p6, 3s2, 3p4. These outer electrons in the third level, these are what we call our valence. And then the inner ones, the ones and the twos, these are called our core. Now, we will never lose our core electrons. Those will never be allowed to be lost. But our valence electrons, we could lose those if we needed to. And so those valence electrons are what are involved in bonding. And so the core electrons represent a noble gas configuration, and those valence are what are involved in bonding. And so if we take a look at kind of what it looks like, again, this is sodium here. And so 1s2, 2s2, 2p6, that's the abbreviated version of, or that's the electron configuration of neon. And so we can abbreviate those configurations if we need to. Now, if we think about the electron structure in the periodic table, I do need to have you memorize these two terms here. Periods are the rows on the periodic table, and the groups are the columns. Now, the way that I always remember this is a P looks like an R, and a C looks like a G, okay? Or a G looks like a C. Period, row, column, group, or group and column. Okay, so that's how I always remember those two. Now, your group or your period represents the outermost energy level. So whatever row number you're in, that tells you pretty much how many energy levels you have. And then your group, sometimes those are called families. Those are your columns, and those represent the valence electrons in the outermost electron level. So if we take a look at this, the numbers here on our row represent the numbers of our electron configurations. And then if you take a look here at the numbers of the columns, you have to do a little bit of thinking, because if we're here at fluorine, fluorine is technically a 2p 2s2. My bad, I'll write it up here. Fluorine is a 2s2, 2p5. Well, if we add 5 and 2 together, we get 7. 7 is our column number. Okay, so that represents our valence electrons. If we take a look at boron, boron is 2s2, 2p1. 2 plus 1 is equal to 3. We get that column number of 3, or we take off the 1 off the 13. All right. Now, again, we can abbreviate those electron configurations. We don't always need to write out all of those letters and numbers. Eventually, when we get good enough at it, we can realize that, all right, if we pass through a noble gas, that finished off a whole row. And so if we take a look here, our group 1 is always in an S1. It's always got an S1. So lithium already passed through helium. Helium was our noble gas. And so we've got helium with a 2S1. Now, sodium is passed all the way through neon, so that's why we put it in brackets. And so then we've got neon, but now we've got that 3s1. Potassium is one further down. It passed all the way through argon, and it has a 4s1. So I'm hoping here that you see this pattern of the S1s for that group 1. The S2s are in group 2. And so these abbreviated electron configurations can help us see those patterns. It also helps us not have to write nearly as much. And so to write an abbreviated electron configuration, you're going to write the noble gas that we already passed through in brackets. You can figure that out by running your fingers along the periodic table and figuring out what electron or what noble gas we passed through last. And then you need to write everything after that. So if we take a look at sodium, sodium is 1s2, 2s2, 2p6, 3s1. In green, I have put neon's electron configuration. Neon is 1s2, 2s2, 2p6. And so to shorten this on up, all we need to do is put neon in our brackets, which tells me I already have 1s2, 2s2, 2p6. But with neon in brackets, all I need after that is that 3s1 to give me sodium. So you do need to know how to write these abbreviated electron configurations. If you can write the normal ones, you can write the abbreviated ones. The normal ones include all the different configurations. The abbreviated, you just take our last noble gas that you passed through and continue on with it. Now, we've got those transition metals in the middle. So far, we have just talked about the first 2 columns and then those last 6 columns. Once we get into the transition metal area, it gets a lot more confusing. So if we start with scandium, which is number 21, we're going to start filling our 4s2. So we're going to have potassium and calcium. So 4s2. Now we're going to actually go down a number into the 3D. And so we're going to go down into the 3D and fill as many as we need. Now the d orbitals can all hold 10 electrons. And after that d orbital, we would go back up into the 4s. So if we wanted to go all the way to bromine, I'll write this up top here. Bromine, I'll pick a different color just a sec. Bromine. Okay, so I'm going to start here with our abbreviated configuration. Bromine, before we get to bromine, the last noble gas that we passed through was argon. So if you take a look and run your fingers to get to bromine, hydrogen and helium, lithium, beryllium, keep on going, keep on going. Argon is the last noble gas that you completely pass through before we get to bromine. So we pass through argon. Then we need to fill in that 4s2 of potassium and calcium. It's going to get kind of weird here. We're going to go down into the 3D, and we've passed through all the d orbitals because we have to go past zinc, so we need 3d10, but then we're going to hop back up into the 4p5. So the d orbital throws a little bit of an interesting curveball into how we number things. We go from 4 down to 3 and then back up to 4 if we need to. So here's some general rules on how that all works. The row of the D subshell is always one less number than the row it is in. So the scandium, titanium, vanadium, all of those are in the 3D subshell. But if you take a look at the row number is 4. Okay, so the D subshell is 1 less than 4, which would give us 3. If you take a look down further, that next in transition metal area is 4D, even though it's in row 5. So we're always going to fill in the row number S, so 4S. Then we'll fill in the row number minus 1D subshell. So if our row is 4, our D subshell is really 3. So 4S, 3D, and then we can pop back up to the 4P. Now our inner transition metal area, which is lanthanum through deuterium and actinium through lawrencium, those are the bottom 2 rows there. What we're going to do there is we're going to add those electrons to an F subshell. Now the F area can hold 14 because we have 7 orbitals. 7 times 2 gives us that 14. So our inner transition metal area down here always is 2 less than the row it's supposed to be in. Now, I know it's tough to think about, but those rows down at the very bottom of the periodic table are actually supposed to slide up into the periodic table where you see that red outline. And so that cesium is supposed to be in the 6th row, but its F block is numbered 4. So those F blocks are always 2 less than the row it should be in. And so if we need to fill these, we're going to fill our row numbered S, then our row minus 2 numbered F, then our row minus 1 D, and then our row number P. Okay, I won't expect you to really go down into those, but I just need you to know that down there we're filling in our Fs. So here's an overall look at the overall electron configuration. I know it's a little bit blurry, but you can see here, these are the ending configurations after all is said and done.